Okay, we have 15 people here. I'm sure more people will join afterwards. Welcome to another talk of Astrophysics Talk series organized by Istanbul University Observatory. Today, our speaker is Rahul Sharma from Raman Research Institute. His master and PhD degrees are from Delhi University, and his main research area are neutron stars, black holes, compact objects, including cataclysmic variables, X-ray pulsars, etc. So he will be giving a talk on AstroSat view of accreting-powered millisecond X-ray pulsars today. So we thank you first for accepting our offer to give a talk here, Rahul. So you can start your talk. Thank you.
Okay, thank you. Thank you for giving the opportunity. So good afternoon, everyone, first of all. So I will present my talk on the AstroSat view of accretion millisecond pulsar. So this is my, I will just divide my talk. Okay, so I will divide my talk in two parts. So first I will give an introduction, then I will discuss about the AstroSat result on two accretion-powered millisecond X-ray pulsars. That is SAX J1808.4-3658, and the second is SAX J1748.9 minus 2021. So the X-ray binaries are astrophysical system which consists of a compact object. So this compact object can either be a black hole or a neutron star, and there is a companion star. So these systems are powered by the accretion of the matter from the companion star to the compact object. So this is a pictorial diagram where the ordinate star or companion star gives matter to the compact object, and this matter falls to the compactor through an accretion disk. When this matter falls onto the pole of the neutron star, then we see the X-ray beam, or we see the X-ray pulsation when we are in the line of sight of these pulses. So these X-ray binaries are generally classified based on their companion mass. So X-ray binary, depending on their companion mass, so they, because of their companion mass, they have different evolutionary states. So their accretion process is different. So generally in low mass X-ray binary, accretion can happen through the Rose-Lobe overflow, while in the high mass X-ray binary, where the companion mass is more than solar mass, or generally over 10 solar mass, these supergiant or very heavy companions are through a lot of stellar winds. So these systems are powered by the stellar winds. In low mass X-ray binary, the companion star is very small, that is less than a solar mass, and they're powered by the Rose-Lobe flow. Depending on their they further classified in their how they are observed. Are they observed in the transient state, or they are observed persistently? So persistent system are those from since their discovery, we see them in the on state. That is the direct, we always see the X-ray coming from those sources. Those are persistent sources. So persistent sources can be in both classes, low mass X-ray binary also and high mass X-ray binary. While the transient system are those systems which are generally not observed during a very short time or for a long time, but suddenly they show the erratic behavior and they show the X-ray emission suddenly from these sources. These are the transient sources. Further, these sources further classified in based on their compact object. What are their compact object? Because depending on their compact, we see different properties from these X-ray binaries. So neutron star low mass X-ray binary show different properties, and black hole show different properties. So neutron star low mass binary can show pulsation, while black hole will not show any pulsation because they don't have any solid surface. Neutron star also show X-ray bursts, which are the surface phenomena, which is the accreted matter is going to thermonuclear explosion. My black hole doesn't show this kind of variation, and they also show different kind of evolution during the outburst period. So in high mass X-ray binary also this classification is there, like neutron star and black hole high mass binary, neutron star high mass X-ray binary. Generally neutron star in high mass X-ray binary observed as a pulsar because they have very strong magnetic field. But in my focus in the low mass X-ray binary transit neutron star, which generally show the pulsation. So these transient LMXB are generally observed during only the outburst period, which is during the cosines. Their luminosity is very low, which is very hardly detectable with like proportional counter. So with a very high sensitive focusing instrument, we can detect these sources in cosines also. Their Cousins luminosity is around 10^31 to 10^34. So this is on the right panel. I show a example diagram of a source where we see that during initially it is like a faint source in coincidence. Suddenly we show an outburst, and suddenly there is an increase in the luminosity of these sources, and this luminosity can be order of magnitude higher. So the luminosity can rise up to 10^36 to 10^38, or so these sources can show multiple outbursts after few days of difference. Can be this difference can also be of the year order. So this is the source which has showed an outburst in 2010 and another outburst in 2015, and these two outbursts are very clear, where we can clearly make there is an outburst, and there's another outburst in 2017. This I will discuss in further in this talk, where I will discuss about the X-ray pulsar, this SAX J1748. So this diagram just show that there is a clear we detect this outburst for a short period of time while the cousins period is very long. So these system give us an opportunity to study these sources at different velocities. So during the outburst, we can track these sources, and we can study at different part of this outburst. So we have this outburst show different kind of velocity, so we can track them, and we can study at what luminosity how the source is behaving and how the source is evolving. So this transient neutron star low mass can be pulsating or can be non-pulsating. So not all neutron stars that we observe in this system are pulsating neutron star. So I will talk about the specific class of this source, which are pulsating neutron star, where they show millisecond X-ray pulsation. So accretion-powered millisecond X-ray pulsar are the part of the neutron star LMHB system. So their spin period is of the order of milliseconds. They can vary from 1 to 10 milliseconds, and they have. So in this system, they have a strong magnetic field. Magnetic field is strong enough so that it can truncate the accretion disk, that is material coming from the companion forming the accretion disk. So this magnetic field can truncate the inner accretion disk, at least a part of the stream of this or part of the material, and it can pull those material to the hotspot of the neutron star. That is, not hotspot, that is a magnetic pole, and will create a hotspot. So accretion coming from this region, and since the neutron star is spinning, when we are in the line of sight of this thing, then we can see the X-ray pulsation. So currently only few sources of this kind of sources are known. Only 23 are known up to now, among hundreds of neutron star LMXB systems. So I will first go to the first source that has been discovered as accreting millisecond pulsar. So SAX J1808-3658 was the first accreting millisecond X-ray pulsar which was discovered. So around 401 millihertz, around 400 hertz spin pulsation was observed from this source with the RXT satellite. So on the top panel, this figure, it shows the power density spectrum of the source from the RXT, and show clear signal at the 401 hertz. And this is a small panel is there. So it shows a spin profile, or this spin pulse profile of the source, which is clearly a sinusoidal kind of shape. Soon after its discovery, its binary nature was also established, and through the Doppler motion delay or the pulse arrival delay, and it shows a very clear binary orbital, circular orbit kind of feature. Around 2 hours, it has around 2-hour orbit with a time delay of around, or some projected time major X around 62 light milliseconds. So this source was latest. It has showed around 8 outbursts since its discovery, and latest outburst was in 2019. So this is its outburst light curve. So it was not observed till 7th or 8th August. After that, it started to show the outburst behavior. So it is started to increase its luminosity in the X-ray band, and it around 30 days, around for 1 month, it showed a full outburst from going peak around 13 to 14 August. So during this period, outburst period, we observed with AstroSat satellite. So we observed this source with the AstroSat during August 14 to August 15. That is around peak of this outburst, around this region, for around 125 kiloseconds with exposure around 49 kiloseconds. So AstroSat satellite has around So AstroSat satellite has 5 payloads in which the X-ray payloads are 2, which are SXT and LAX-PC. So SXT is a soft X-ray telescope which focus on 0.3 to 8 kV, while the LAX-PC 3 to 78 kV. So LAX-PC is a large X-ray proportional counter area, which is a proportional counter which has a large collecting area, and it has a very good timing resolution around 10 microsecond. And while SXT is a focusing instrument like Swift XRT. So we use the data from these two instruments on board AstroSat. So as it is a millisecond pulsar, so first we started with the search for the pulsation in this source. So this source show a very strong pulsation. So if we do the fast Fourier transform and see the power density spectrum, it will show a clear peak around 401 Hertz. But since it is a binary pulsar, it has a binary orbit, so these pulsations sometimes smeared out by the binary orbital motion. So we correct for its binary orbital motion, where there is a time delay because of the binary period. So this is called as a orbital delay or binary or Doppler delay or binary orbital delay. So this is caused by the delay can be of the order of the millisecond, was around 60 milliseconds, which is the projected sum major axis of this source. So first we corrected it by knowing the beforehand we know from the previous observation of the period, its orbital period and the projected sum major axis. So we corrected for the ascending time node. So by correcting the ascending node and searching for the pulsation, so we had 2 parameters to change, that we change for the ascending node and we change for the spin period. So by searching in the two-way grid, we found the ascending node and the we found very strong coherent 401 Hertz pulsation at this frequency. This is the correct period after correcting the binary motion. So after that, we created the pulse profile of this source to see how the pulse behavior is there. So we created 3 to 30 kV pulse profile. So we created this 3 to 30 kV. This red one is the overall 3 to 30 kV pulse profile, and we fitted this profile look like a sinusoidal, but it has actually 2 components. There is this profile can be fitted with with one fundamental sinusoidal function and its harmonic. So the fundamental that we found, it has a fractional amplitude of 3.3%, while this harmonic has a pulse fraction around 1.3. That is the amplitude of this sinusoid. So next we studied how these pulsation depend on the energy. So we created the fraction, we divided the full data in different energy band and created this pulse profile and study how this fractional amplitude and its phase lag changes with the energy. So the left panel show the fractional amplitude with the energy. So this dark black one is the fundamental, and the gray one is the harmonic. It's harmonic component. So the fractional amplitude in the low energy is higher, and with the increase in the energy, the fundamental amplitude decreases, while the harmonic component start to increase, and around 10 kV they both become significant. Their contribution become nearly equal. If we see the phase delay or the time delay, we found that the fundamental has a negative lag, while the harmonic has a positive lag. So both have a different lag in the full energy band compared to the first energy band. So these things has been observed in this source in previous outbursts also, like 2015 and 2019 also, with the nicer satellite. So this kind of behavior is already known in this source. So before going to the spectrum analysis, I will just briefly describe how the emission how the emission is coming from this system, Loma Survey system. So this system consists of mainly 3 emission components, which is the accretion disk, neutron star surface, and the corona. So accretion disk, that is forming this disk can be modeled with the multicolored disk black body component, that is this BB this model is available. And second component, neutron star, which we can model with a single temperature black body. And third is the corona, which can be described as a thermal componentized emission, where this soft photon from the neutron star surface or the disk can go to the corona, get upscattered, and we see a hard emission, So this hard emission can be a power law like shape. So the distribution is a power law like. So the input of this corona, or the input to the thermal component emission, can either be a neutron star surface or can also be a disk. So depending on the shape of the corona, so this emission changes. So the contribution of the seed photon changes depending on the seed where the disk is where the disk is riding, in the shape of the corona, where how the corona is distributed. Apart from that, we get the reprocess emission. So the emission from this corona can go to the disk and get reprocessed, and we see a iron emission like feature in these sources. So this is an overall geometry from the low mass X-ray binary system. So we created spectrum from the SXT detector and the lag species detector, and we simultaneously model both spectrum. So this is a black one is a SXT spectrum, red one is the lag species spectrum. So lag species is has not very good spectral resolution, so we can't resolve the iron emission line in this spectrum. So we tested different kind of combination of the model, like thermal black body plus accretion disk, and with combination of the corona or thermal componentization emission, different combination, and we found that all three this spectrum can be well fitted with the all three component, where the accretion disk component, which has the temperature around inner disk temperature around 0.9 kV, and neutron star surface temperature around 1.4 kV, and the thermal componentization emission, which is coming from corona, is around 1.5. That has spectral index around 1.5 kV, and the corona temperature was very high, around 100 above 100 kV, which cannot be detected because this band pass is below 50 kV or something in this lag species data. So in this case, we found that if we use the seed photon from the neutron star surface, it can be well modeled. If we use the seed photon on the disk, we get a worse fit than this one. So this is our best fit, where the seed photon from the neutron star surface is considered in the corona, and which get upscattered and produce this hard X-ray emission. So in conclusion to this work, we found that this outburst was a very long, around a month outburst, and we found the broadband spectrum can be well fitted with a combination of three emission components from the accretion disk, neutron star surface, and the corona. And this has been previously observed with the broadband spectroscopy, like from the neutron star and the X1 plus neutron star also. And we found a very strong coherent pulsation around 4.1 hertz with the AstroSat. And we found its orbital solution was compatible with the previous study. Like the solution we get from the lag species data is very consistent with the Bult et al. And we found the pulse profile can be well fitted with the 3 to 30 kV pulse profile. Average pulse profile can be well fitted with the two harmonic related sinusoidal function. So it's the fundamental component has a functional amplitude around 3.3%, while the harmonic had a functional amplitude of around 1.3%. And we also find a very strong dependence of this pulse fraction and the phase lag or the time lag of these pulses with the energy. So this work is currently in preparation, and we soon will submit into a journal. So coming to the next source, which is SAXJ 1748.9 minus 2021. So it is also a different MXP. This source is located in the global cluster NGC 6440. It shows pulsation at 442 hertz, and it has orbital period around 8 hours, and projected SMJ of 387 light seconds. It has also shown multiple outbursts after the SXJ. It is the second source which has shown more than 5 outbursts. So I've already shown this outburst light curve from the maxi of this source. So it's a 2010 outburst, then there is a 2015 outburst, and there is a very faint outburst in 2017 of this source. So if we compare the 2015 and 2017 outbursts from the different observatory like XRT, which are very focusing and have lower small field of view. So this is the outburst of 2015 traced by the Swift XRT. So where the peak luminosity goes up to 8 into 10 to 37 lux per second in 2015 outburst. While if we see the 2017 outburst, where this black one is the Swift, this is the maxi point, black one, which is shown here. If we zoom in to this part, and this red one is the Swift XRT. So Swift XRT could not caught the source during the rise phase. So it start observing the source during the decline phase. So during the outburst, the peak luminosity of this source was observed to be 10 to 37, around an order of magnitude lower. So this outburst was fainter and it was also shorter. So this outburst lasted around 13 days only, while this outburst was lasted around 2 months, approximately 2 months. So there's a clear-cut difference between the two outbursts. So the 2010 outburst and 2015 outburst has similar kind of properties, but 2017 outbursts are totally different from its previous outbursts. So we observed this source with the AstroSat during 2017, and so we studied spectrum with the same Swift XRT and the LAX-PC, and we could model it with the simple black body and the NTH component. So these two models were sufficient to model it. So the black body component was found to be around 1.1 keV, and the photon index was around 1.6. It was also showed a hard X-ray, clearly hard X-ray hump is there. This is actually because of the detector of the LAX-PC. It is due to the xenon edge, because this LAX-PC proportional counter is filled with xenon gas. So this is coming because of the detection calibration. So we model this as a Gaussian. So next, I forgot to show you. So during this observation, so this black gray region is the AstroSat region where it is observed. So it has been observed around 200 kiloseconds. And in between, the XMM also observed this source during this outburst. So there is an overlap of 57 kiloseconds during these two observations. So this is the average spectrum from the full AstroSat observation. And this is the spectrum from that overlap region, or for that 57 kilosecond overlap region. So if we include the XM Newton spectrum, we can clearly see there is an emission line with XM Newton spectrum, because it has a very good spectral resolution. So we can detect a very narrow emission line, which is coming from the disk because of the reprocessing of the emission from the disk. So if we include the XMM spectrum, the SXT and LAX-PC, so same model can be well fitted with the black body and nth comp. Nth comp is a thermal componentization model. And the residual also shows 6.5 kV error emission. So this feature has also been observed in previous outbursts, like 2015 outburst. And during the same outburst, where with the new star and XM also, this has been detected. So to model this feature, we used a reflection model. It is a non-relativistic reflection model, Silver CP. So beside this, we added this thing. So this is a hard X-ray emission like NTH comp that is going to the disk and get reprocessed and get emitted. So if we see, you can say this is the emission components coming from the silver. So this is the black body, and this is the NTH comp that is coming above that, and this one is the silver component which we use. So if we use the silver component, then we can know about some properties of the disk, that is ionization properties and the iron abundance. So iron abundance is well consistent with the solar abundance order, and we found the ionization of the disk is around 3.5. So next we started to search for the pulsation. So the outbursts were very faint, and the source was very in a faint state during this observation. So when we started to look for pulsation, we couldn't detect any pulsation with the fast Fourier transform power spectrum. But after correcting for the binary orbital motion, so we started to correct for binary orbital motion. So last outburst was in 2015. So we used the 2015 values of ephemeris, and we started to look for observation. So then we started to search, and then we use the same value of orbital period and projected semi-major axis. We just changed the ascending time node, and we started to look for pulsation. So we search for different value of ascending node. So this is a plot which shows the epoch folding result for different ascending node. So we found that at this value, we can detect a very clear pulsation where the chi-square is maximum. So with this pulsation, we again look for a best. With this epoch, with this we updated the epoch, and we started to look for average pulsation from the full data set and found the average pulsation at this hertz. So as the source was very faint, we could not do the energy resolved study in this case, because if we divide into different energy, we will not able to see the any pulsation. So we could divide into these two energy band, 3 to 7, 7 to 20 kV, and we could detect a significant pulsation in these two cases. So this above panel is a 3 to 7 kV pulse profile, while the below panel is 7 to 30 kV pulse profile. So 3 to 7 can be well fitted with a single sinusoidal component, that is fundamental. While for the 7 to 20 kV, we can detect its harmonic also along with the fundamental component. And this fundamental amplitude, the fractional amplitudes were around 0.5% in both energy band. Along with this, we also detected an X-ray burst in this source. Unfortunately, we could not detect any X-ray burst in the SXJ1808, but in this case, we could detect two X-ray bursts. So this is the profile of these two X-ray bursts. So X-ray bursts occur during this accretion process when the enough accreted material is stored on the neutron star surface, and there is a thermonuclear and runaway. So this is a persistent emission, and suddenly there is an increase in the emission. So the shape is very fast rise. So because of the thermal runaway, so there is a very high increase in the luminosity, and after that it will start to decay gradually, exponentially. So we model these profiles in different energy range. So this is the decay time of these bursts in different energy range, like 3 to 6. We divide into 4 energy panel, and this is which show that this burst decay time gradually decreases with the energy. So that this suggests that with the energy, it is start to cool. Means as there is a gradual increase. So with the different energy show a very different decay time. So this black one is 3 to 6. This is red is 6 to 12, and so in this case we show the 4 energy spectrum, that is 3 to 6, 6 to 12, 12 to 18, 18 to 24. In this insect one, we show 2 higher energy band, that is 24 to 30 kV and 30 to 40 kV. So generally these bursts show emission up to 30 kV, but in this case we detected a burst emission. In this case, as you can see, there is a burst detection above 30 kV also. In this case, there is no detection of the burst, while in this case, this clear detection of this burst above 30 kV. So in this case, we found that the second burst does not show a very peculiar or very general behavior of this X-ray burst. So we started to do the time resolved spectroscopy. So we performed the spectroscopy from 3 to 40 kV band with the LAX-PC data. So we divided each burst. We extracted the spectrum from each 1 second of this burst and fitted each spectrum with the black body model. And we show this evolution of the black body temperature and the radius. So top panel show the count rate of the burst, how the burst is changing. The second panel is the temperature of the black body component. Third is the normalization, and the fourth is radius. Radius is calculated from the normalization. So normalization depends on the emission radius of this black body component. And fourth is how the flux is varying. And fifth is the fitting statistics, which is in the fitting statistics. So for the burst 2, again, we found that this black body emission show a complex evolution. So it started to increase, then decrease, then become a nearly constant. While we could not see any this kind of behavior in the burst. So generally, some bursts show a very elective this kind of behavior where they show increase in the temperature, then decrease, then again increase. These are different kind of X-ray bursts which show photospheric expansion. So where the photosphere expand and it's get cooled down and then again settle back to the neutron surface, and then again the temperature start to increase. But in this case, we only detect this behavior, that like complex evolution, only in the emission radius, but not in the temperature. So just to conclude this thing, we found that this 2017 outburst has a different kind of properties with respect to other previous outbursts. Like 2015 outburst lasted for around 2 months with peak luminosity on 10^38, while the 2017 outburst was very short one, like 13 days only, and with a peak luminosity around order of Fenter. This was outburst was a order of Fenter and had a peak luminosity on 10^37 hours. So if we see its property, if you compare its property with all other previous outbursts, the only 1990 outbursts show this kind of behavior, when 1919 outbursts show around a 15 days outburst with a same order of peak luminosity 10^37 hours. So so we studied the 2017 outburst with spectrum. So spectrum, we found it to be hard state, which show a very emission up to very high energy, like 1780 kV, and we could detect an iron emission line from the XM Newton observatory. So this emission line is coming from the accretion disk, which is a reprocessing of the hard X-ray photons. With this very faint state, we could detect a 442 Hertz pulsation, and the orbital solution was compatible with this previous observation. Although the signal was not very strong, so we could not do the energy resolved analysis in this case. So we created the pulsar in two energy band, 327 and 720, and we found the fractional amplitude of the fundamental component in both energy was around 0.5%, which has not been observed in this case. This kind of behavior, like in both energy, in low energy and high energy, the fractional amplitude is nearly constant. But generally, this fractional amplitude is observed to be either increasing or decreasing. That is, it is found that this fractional amplitude of the fundamental from the indifferent energy is actually energy dependent. In this case, it has been, in this source particular, it has been found to be increasing with the energy. But in this case, we found very constant. Since we detected the pulsation at very low luminosity, so we could put an upper limit on this magnetic field. So we could put a magnetic field at the pole of around 3.2 Gauss. So this is an upper limit. So magnetic field should be lower than this value. This upper limit is consistent with the previously calculated upper limit on this source, magnetic field of this source. Other than that, we have detected two X-ray bursts in this source, where second burst showed a hard X-ray emission, where the emission is detected in 30 to 40 kV band also. So this emission actually coming from the upscattering of this soft photon that is coming from the burst. It get upscattered because of Compton's upscattering from the hot corona that is present in this source. That hot corona has a temperature above 15 kV, so it can emit this. It can upscatter those soft photon to even higher energies. And the same burst also showed a complex emission in the black body emission radius. This work has been published in this paper. So I'll stop here. Thank you.
Thank you, Rahul. It was very nice talk. It was very nice introduction. And actually what I see is you have done almost everything what you can do with the data.
Yes, yes.
You found pulsations, you did spectroscopy, timing analysis. So very nice job.
Thank you.
So is there any question from audience? So does AstroSat have simultaneous observation with other satellites? Is there any plan?
Yes,
on
yes.
this?
There's some group which are planning to. They have also observed with NICER, AstroSat plus NICER.
These particular sources?
Not these particular sources.
Okay.
Like Newton star low mass experiment in the black hole also, they have planned NICER plus the AstroSat observation.
Okay. Is there any question? I see one. Yeah, Şölen Balman.
Hello.
Yes.
Okay, so let me save the day. I had a question. So can you go back to the very last slides? Yeah, somewhere there. When you showed us the evolution of the radius and temperature and so forth.
Yeah,
that
this one. Yeah.
There, I just noticed something. It's a very brief question, actually.
Okay.
Here, you have this 40-second evolution, and this is the entire burst evolution, 40 seconds.
Yes.
Yeah, okay. And in the radius here, as I see, the radius expands, and I don't see any contraction here. So is it very normal there? It looks like the radius has expanded and stayed towards the end. So go entirely.
So it is like a
bloated.
So it is like if I'm emitting full surface, it become constant. So it is generally represent the.
But it is bloated then compared to where it starts from. So is it? Does it stay bloated? Is that does that mean that?
You were asking about the higher part.
Yeah. See, but what I see in the evolution in the radius is that the what you expect from the temperature is it okay gets hot and then cools over time. So that's sort of something regular. But what I see from the radius is that it sort of it does a wiggle. Okay, it does a wiggle, and then it's again expands a bit and then stays like that. It then tends to go down a bit, but then it looks to me like as if the radius expands and stays bloated.
So it is generally like it starts at a hot spot.
Very common that you see. I would think that it should contract a bit at the end, or maybe not. Am I mistaken?
So generally it is observed like, so it starts with the hot spot, so radius start to increase, and when this thermal was spread to the full Newton's surface, then it become a constant, like in this first shown kind of this way. There is another class where this expansion, when there is a radius expansion is there, that photosphere expands. So the photosphere leave the Newton's surface. So its emission radius increases.
The radius here, whatever is expanding. Okay, the part or spot or the part which is expanding stays bloated, as it seems from these plots.
So it started to
increase. It expands. It looks like it. Okay, the temperature
come back.
It's okay, Rahul. I'm not like trying to create something, but from what I see, the temperatures increase, so it basically sort of gets bloated and then stays that way. The temperatures decrease. The radius does nothing. It should do constant radius cooling. I can understand that, but should that be at the constant bloated radius, or a radius perhaps a bit smaller? I would presume, but maybe I am wrong. Maybe some people in the audience would like to correct me or something. Rather, it's okay. I might be thinking incorrectly, but I thought like the radii, looking at that, I thought it's interesting. Like it's staying bloated rather than it's sort of getting contracted at all. So there's some.
The emission is coming from So after some time, the emission is actually coming from the full surface. So it's full surface radiating. So then
the increase is not
the emission will become constant.
Like radius become constant. Starts from the spot and then entire surface. So then the radius, the effective radius is increasing because of that, and towards the end, the entire surface is emitting all the time.
Yes. And it will just faint slowly. It will cool down. Full surface emitting, but it will start to cool down.
Okay, thank you. So I thought I'll ask that. Thanks a lot, Rahul.
Is there any other question? If not, we thank Rahul again. Thanks for accepting our offer. So it was a very nice talk. So see you on next Monday in our next talk. It will be announced later on. So bye for now.
Okay, thank you everyone for listening.
Thanks, Rahul.
Thank you, Rahul.
Thank you, everyone.